T-minus 10, 9, 8, 7, 6, 5.
In 1977, the greatest adventure in space exploration commenced.
We have ignition, and we have liftoff.
Our eyes, our minds, our souls are moving out through the universe.
You can only do things for the first time once. And Voyager kept doing things for the first time over and over again.
2 robots were built to be able to think and explore by themselves in the deep reaches of our solar system.
None of the managers really appreciated the complexity and the autonomy that we just launched into space.
Yet both missions went seriously wrong only moments after taking flight.
We thought that we'd lost the spacecraft.
They went on to make astounding and unexpected discoveries.
When you see things that you did not predict, that's when there's the most to learn. We were just seeing that time after time.
The Voyagers were the creations of NASA's Jet Propulsion Laboratory, where a brash young scientist had just been put in charge.
I guess there's an obvious question, which is what about the lab itself? What about its people, its organization? Are sweeping changes imminent?
His ambition was to take the next steps in exploring the solar system. Instead, he found himself struggling for JPL's very survival.
And the greatest exploration was going on. It's the very time that the program was being strangled.
This is a story of triumphs.
I just kept saying, what's that? What's that?
And setbacks.
It's not there. What's all this noise?
Most of all, this is a story of perseverance by people and machines struggling against forces put in their way. The stuff of dreams, beginnings of the space age. Next. On March 31st, 1976, the employees of the Jet Propulsion Laboratory gathered to witness a ceremonial change of command.
Good afternoon, and welcome, ladies and gentlemen.
Presiding over the event was Caltech's President Harold Brown, who offered generous praise for the outgoing director, William Pickering.
Having this large-scale open-air gathering was not Dr. Pickering's idea, but I persuaded Bill that 21 years' service could not go unmarked.
No one, neither before nor since, has served in the post as long as Bill Pickering. Many JPLers had never known another leader, and he was widely admired, if not beloved.
Bill Pickering was revered. He was Mr. JPL. When he retired, everybody wore Mr. JPL badges that had a cartoon image of him on it. So it was a real earth-shaking event to have a new director.
Thank you. You know, it seems to me that this last couple of weeks, I have been spending quite a large fraction of my time saying goodbye to you. Of course, it's been an opportunity to think about the laboratory and what we have done. And Bruce, in thinking about the laboratory which you're going to take over, what are the initial conditions? What is the starting point for this? Well, first of all, the assets of the laboratory are these people in front of you.
Pickering was a Caltech professor who had helped JPL develop the Army's first generation of strategic missiles. In 1954, he was named the lab's director.
Because of the advanced state...
During his tenure, JPL built and helped launch the first U.S. satellite. It was only the beginning of an impressive list of achievements. JPL spacecraft were the first to touch the moon for the United States. The first ever to fly by another planet. And the first to orbit another planet. These and other accomplishments had not come easily, and not just because of technical challenges. The transition from building missiles for the Army to becoming in 1958 part of a new federal space agency called NASA had been difficult. There was often an undercurrent of tension between Washington and Pasadena. Some of the discord was personality-driven, but many disagreements derived from the uniqueness of JPL. While the laboratory's land and buildings are owned by the federal government, the staff are employees of one of the world's most prestigious universities, the California Institute of Technology. Given its academic tradition, JPLers were and remain as independent-minded as they are inventive. The same could be said of the incoming JPL director, 43-year-old geologist and Caltech professor Bruce Murray.
Fixing the planet and clouds that move in the planet.
Murray had previously been a member of the mission that captured the first close-up images of Mars. It was one of 4 planetary missions in which he played a key role. From these events, he had experienced the lab from the inside out. Yet, in many ways, Murray was an unusual choice. His resume listed no management credentials. He was a scientist, not an engineer, and he was known as a contrarian, with a reputation for brash outspokenness.
You don't know what you're going to see. Bob is unimpressed with what you're going to see there. I am too.
And now in 1976, Murray's charge was to revitalize the lab and to drum up new business. For the pipeline of new missions was alarmingly thin. It's easy to run a lab, he declared. What's hard is creating the future.
Pickering stepping down is an opportunity to bring in some fresh views, and that maybe the lab could use a little shaking up. Maybe it could use a little fresh breeze to kind of blow out some of the leaves in the corners. In that sense, they chose the right man in Bruce Murray, because Murray was, if anything, a fresh breeze, and perhaps a very stiff breeze.
Well, good afternoon. Let me say at the outset, I don't have any more shoes to drop. That what was announced last Friday is the whole story in broad outline.
4 months into the job, Murray announced a major reorganization. He abolished positions, created new ones, moved people, and fired others. It was a bombshell for employees unaccustomed to abrupt changes. And the timing of the shakeup was especially perplexing. It came right in the midst of JPL's critical role in putting the Viking landers down on Mars.
Murray was very oriented towards, let's think 10 years down the road, 20 years down the road. Let's try to have a long-range plan in place so that we're not just kind of making it up year to year. But at the same time, there is this sense of perpetual crisis, and he always feels like there's this immediate crisis at hand. If we can just get through the next 6 months, or if we can just get through this next year, then everything will be great. Good times are just over the horizon. And it's this very funny contradiction between wanting to have, stable long-term plans, but in the short term, it's this just constant ferment and turmoil.
And so we're in the anomalous position of riding a crest of success and at the same time having to take rather bitter medicine at times in order to extend that streak into new areas and into the future.
Though he did not know it, Murray had just articulated the major theme of his time as JPL's director. His years would be the best and worst of times. The world would witness one spectacular achievement after another. Yet behind the scenes, there was often the threat that JPL might never again build a spacecraft to explore the solar system. Years later, Murray would look back and say, "I had no idea about what I was getting into." Long before Bruce Murray's appointment, it was known that it was possible to use the gravitational force of a planet to alter the path and increase the velocity of a spacecraft.
There's a lot of elegance in the way the planets move. And when organizations like JPL get smart enough to take advantage of it, there can be elegance in how we go.
Under the right conditions, a spacecraft could slingshot its way from one planet to another, what came to be known as gravity assist. Then there was another discovery. In the latter part of the 1970s, all of the outer planets would be aligned on the same side of the Sun. That would allow for a spacecraft launched towards Jupiter to use gravity assist to journey on to Saturn, Uranus, Neptune, and even Pluto. Most exciting was the knowledge that this planetary alignment was rare, occurring only once every 176 years. The next opportunity would not occur until the middle of the 22nd century. It was the chance of not one lifetime, but two. And in 1966, JPL mission designers mapped out an ambitious mission they named the Grand Tour. 4 highly sophisticated spacecraft would be sent out to reconnoiter the outer planets.
So we had this concept of an outer planet spacecraft that was radiation hard, had nuclear power, had the capability to repair itself.
But the Grand Tour came with a grand price tag of $1 billion, the equivalent of $7 billion in today's dollars. That was unaffordable, and in late 1971, the Grand Tour was canceled.
That was clearly a shock because this was the one opportunity in 176 years to do it. And so the team at JPL looked at a way to build a simpler spacecraft, a lower cost spacecraft. What was originally the Grand Tour became Mariner Jupiter Saturn 1977, with a limited 4-year goal with the possibility of continuing on if we were successful.
The revised plan cost only 1/3 of the original proposal. It was a budget that NASA believed it could afford, and the agency gave the revised project a green light. At JPL, work quickly got underway to build 2 spacecraft that, while not as sophisticated as those first envisioned by the Grand Tour, were still tremendously challenging. Compared to previous missions lasting only weeks or months, these spacecraft would have to operate for years. Greater distances meant upgrading communications to transmit commands and receive data from the 11 science instruments carried on board. And a new energy source was required, small power plants that generated electricity from the natural radioactive decay of plutonium. The greatest challenge was making the spacecraft highly independent and self-sufficient. They were intended to be the smartest robots ever created, designed to think and act on their own.
This spacecraft, more than anything else, required it be really intelligent and autonomous. It had to diagnose itself. 2 master computers, 2 brains, all the time. This one's running the spacecraft with all the software. This one over here is in parallel keeping up with it. And if necessary, and something goes wrong, the first thing you do is switch brains.
The concept of redundancy was applied throughout the spacecraft. The result was a machine with 5 million electrical parts. In the midst of development, there was disturbing news for each of them. NASA's precursor missions to Jupiter and Saturn, Pioneers 10 and 11, discovered that Jupiter was surrounded in intense radiation that could easily fry unprotected electrical circuits.
So we got into trying to struggle with that really, really hard, designing shielding and spot shielding and box shielding and going through the whole system with a fine-tooth comb, we'd already committed to the design, and now we realize that we got a radiation environment, and now how are we going to deal with that?
And then there was JPL's determination to build a spacecraft capable of reaching Neptune and Uranus, a goal not openly discussed.
We had to be very careful that we did not expose what we were doing in a way that appeared that it was unnecessarily driving the cost of the fundamental mission. And so most of it we, I think, honestly rationalized was risk reduction in terms of reducing the risk of the Jupiter and Saturn mission. But in so doing, it also enabled the capability that we were going to require to go to Uranus and Neptune.
Even before becoming the mission's second project manager, John Cassani was scheming about ways to get to Neptune and Uranus. He had taken part in a minor engineering conspiracy that would have major and literally far-reaching consequences.
While I was in the division, we came up across the fact that our sun sensors were going to be marginally operative just past the range of distance of Saturn. And so we decided in the division that we would take it on ourselves, even without talking to the project manager, to change the design of that sun sensor by adding a little operational amplifier. It wasn't a big change, but still we had to do something different. But making that one change would guarantee that the sun sensors would work out beyond the orbit of Neptune.
Cassani also thought the spacecraft were so special that they were deserving of a new name. He advocated, and NASA agreed, to call them Voyager 1 and 2. Another decision Cassani made was to no longer hide the fact that an American flag would fly aboard the spacecraft. In the early days of the space race, when the odds of success were low, touting the stars and stripes had been officially frowned upon.
We had developed a clandestine practice of sewing flags between the thermal blankets of spacecraft. We didn't advertise that. Nobody knew about it for the most part. I decided to get this out in the open. This project here represented not just the efforts of the people that worked on it, but this was an American enterprise. I mean, we had contractors from all over the country. We had taxpayers in every state that had contributed to what was here, and so it was an American product. That's what the flag was meant to symbolize. Made in America, that's what that was.
In July of 1976, the much-anticipated launch of the Voyagers was still a year away. Managerial credit for their development belonged to Murray's predecessor, William Pickering, but they would be Murray's to fly. The same was true for the two orbiters that had just ferried the Viking landers to Mars to search for signs of life. They had been built on Pickering's watch. Before becoming director, Murray had been a critic of this mission, believing the technology did not yet exist to identify the signatures of life. But now he saw the landings as a public relations bonanza to build support for the next missions he wanted to fly. That was becoming harder to do, for the days of unwavering support from Congress were now just memories.
I can remember in 1965, after Mariner 4, when we went back to Washington, and Bob gave the presentation to President Johnson, and I ended up presenting it to the House and into the Senate Space Committee. And the senator from Mississippi, Senator Stennis, was chairing the sessions. And so I went through the little play with these pictures, which most of you must remember, looked a little bit like moldy wallpaper, but anyway, we drew some profound conclusions from them, and it was over, and as I was going out, Senator Stennis got up and said, "Son, I didn't understand a word you said, but it was great." Well, I think you realize that those days are over where the achievement alone appeals to this nationalistic rivalry with the Soviets.
NASA was now in the process of reinventing its human program. betting its future on a reusable space shuttle, and a policy that Murray believed was fraught with faulty thinking.
At that point, NASA was one-dimensional as an agency, and that was to develop successfully the space shuttle. It had been developed to be a government monopoly run by NASA. The only way you'd be able to get into space was using the shuttle. This is for cargo. This is for communications. It was nuts. It was a patently absurd idea.
The shuttle could haul a payload only as far as Earth orbit. To send a spacecraft further required another launch from low Earth orbit using a second rocket. That made the shuttle an especially poor match for deep space missions.
When I came to JPL, I realized this was threatening the whole planetary program, and that was my business.
Developing the shuttle was an immense task. It was running over budget and behind in schedule, putting pressure on NASA's other missions. One was an ambitious space telescope that in time would come to be known as Hubble. It too was pushing boundaries of technology and costing more than planned. With bills mounting up, NASA lacked the funds to support the shuttle, a space telescope, and ambitions for the next planetary mission. A spacecraft intended not to just fly by Jupiter, but to orbit the planet. In 1977, the Jupiter mission was singled out for cancellation. If that happened, there would be little for JPL to do. Murray decided he had no choice but to go on the political offensive to save the Jupiter Orbiter Probe, or JOP, as the mission was first called.
I undertook a personal political mission to go to Washington and deal with it and organize an attempt to beat the chairman of the Appropriations Committee on the floor of the House in order to get JOP in.
The start or non-start of the Jupiter Orbiter Probe mission had to be voted on individually in the form of a roll call by the entire House of Representatives.
We marshaled all our forces, got help from lots of different quarters, and when all the smoke cleared, we actually beat the chairman on the floor with an up-down vote on this mission.
As all of you know, we won that one going away 280 to 131. It was an extraordinary victory and quite unexpected by all the players, both the professionals and the amateurs like myself and others.
Well, that's good news, in the sense it's a victory that, David beat Goliath. It really was. And that's how the newspapers picked it up. But Goliath isn't really dead.
Murray's campaign was a brazen move that infuriated the leadership of NASA and members of Congress. But he may have been emboldened by something that wasn't publicly known for years. Earlier in 1977, Jimmy Carter had become president, and that spring, Carter's science advisor had asked Murray to become the next NASA administrator. Murray, lacking the temperament to cope with bureaucracy and being no fan of the shuttle, made it clear he was not right for the job. Besides, from JPL's mission control, one of the greatest adventures of all times was just about to have its first encounter, and Murray would be at the helm of it. What job could be better than that?
T-minus 15 seconds and counting. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have ignition and we have liftoff. We have liftoff of the Titan Centaur carrying the first of two Voyager spacecraft to extend man's senses farther into the solar system than ever before.
Although launched first, this spacecraft was named Voyager 2 because its less efficient trajectory meant it would arrive at Jupiter and Saturn after Voyager 1. Voyager's programmers had taught the spacecraft that if it sensed anything unusual, to switch to backup systems, And that's exactly what had already occurred. Engineers call this fault protection.
The fault protection started doing its thing, reconfiguring the system. We're still attached to the launch vehicle. It's in the early stages of its flight, and the first thing we see are the gyros being swapped.
Gyros provide a sense of balance and orientation, and Voyager 2's gyros believed something was wrong. That was because JPL engineers had not prepared Voyager for how rough a ride the launch would be.
The launch vehicle, as part of its powered flight, went through a roll. And the spacecraft would never have done that on its own, so the spacecraft thought that was a fault.
I think there were 6 or 7 different states that it went through in trying to correct the fault. Well, soon I can't have 2 gyros fall. Must be a computer that has failed. It switched out. We had redundant computers, so it switched out computers. Well, it can't have been that. It must have been something else. So it went through this whole sequence of trying things, and we thought, holy mackerel, this spacecraft looks like it's going bonkers. And we thought that we'd lost the spacecraft.
Finally, we got to separate from the launch vehicle and we were on our own, but the problems weren't over.
The boom holding science instruments appeared not to have locked into place. And far worse, the spacecraft was now slowly tumbling. A last-ditch suggestion was made to stop the computer and reboot. But Chris Jones knew that then the spacecraft would be unable to lock onto the Sun to properly orient itself to head on to Jupiter, and that would mean a lost mission.
I knew that part of the story as well as I knew my own name. And when I heard the recommendation come from Pasadena that let's send that to air, I knew instantly that that was the wrong thing to do. Now, I had to convince people who were still mystified as to why anything was happening. But I think Glenn believed in me, as did John, that we shouldn't do that, and so that was the decision that was made.
The Voyagers were designed to take care of themselves in the far reaches of space. No one thought the first test of its ability to survive on its own would happen in the early hours of the mission. But that is exactly what it did. After swapping thrusters, gyros, and finally the computers, Voyager 2 stabilized. But another hour passed before the sun sensor locked onto our home star.
I remember reading the LA Times the next morning. Headline said, "Computer wars in space." Oh my goodness. What are the people going to think about what we're doing here? The spacecraft and the computer system did exactly what it was supposed to do. It outsmarted us.
None of the managers really appreciated the complexity and the autonomy that we just launched into space. Bruce Murray cornered me outside the conference room and made a remark that I'll never forget. He said, "I never knew that we could build things like that at JPL." He was just overtaken by the complexity and the ingenuity that the Voyager spacecraft had.
Two weeks later, the launch of Voyager 1 had its own scare. This time, though, the problem wasn't with the spacecraft, but the launch vehicle. The first stage Titan underperformed, requiring the computer aboard the second stage rocket to compensate with a longer burn. When this second burn ended, placing the spacecraft on its trajectory to Jupiter, only 3.5 seconds of fuel remained. 3.5 seconds had separated success from failure. These near-fatal events in just the first minutes of flight were hints of what was still to come for the Voyagers. The Voyagers were just underway, but already they had caught the imagination of the world. England's Prince Charles was only one in a long line of dignitaries, celebrities, and politicians wanting to take part in the Voyagers' adventures to the outer planets from Mission Control in Pasadena.
Station 43, this is Voyager Command.
Voyager Command, 43.
Please turn command modulation on at this time.
Roger, stand by.
The spacecraft promptly responded to the Royal Command, but the Voyagers weren't always so obedient. Even after the difficulties of the launches, mission engineers were still underestimating the complexities and independence of the machines they had created.
And because they were so smart, it took a lot of time to learn how to fly these spacecraft. So initially, for the first 6 months, we were constantly trying to catch up in our learning how to fly these spacecraft safely.
A problem with Voyager 2's thrusters was causing it to behave erratically. And then an issue cropped up with Voyager 1. Its scanning platform that moves the spacecraft's camera and other science instruments was refusing to budge. Engineers became so focused on fixing this problem that they neglected to send a routine but vital transmission to Voyager 2.
We did not send a necessary command to the spacecraft, and it thought its receiver had failed, and it switched to the backup receiver, which had failed.
Through inappropriate actions by the ground system, we lost one of the Voyager 2 receivers. Fault Protection stepped in again and saved the day there.
For 7 days, all contact with Voyager 2 was lost. But after the week passed, the spacecraft switched back to its partially functioning backup receiver, as it had been programmed to do. But relief that contact had been reestablished was tempered by knowing that for the rest of its life, Voyager 2 would be essentially tone deaf. To hear instructions from Earth would require special frequency adjustments. And should the backup receiver fail, Voyager 2 would be unable to receive any further commands, and the mission would be lost.
Lab management was concerned at the ability to fly these two spacecraft, number one, for their complexity, and two, the fact that many of the talented people that had participated in the design were now off the project.
After finding a solution to Voyager 2's receiver problem, the engineering team went back to tackle the stuck platform on Voyager 1.
It seems like the more commands we send, the easier it seems to move, like it may be slowly working through whatever.
The next concern was enduring the intense radiation surrounding Jupiter. Flying too close to the planet for too long could be fatal for the Voyagers.
We knew we wanted to go by Io, so we had to have one close pass of Jupiter and take a dose.
Radiation was only one of many considerations in deciding what corridor through Jupiter and its moons the Voyagers should take.
If you looked at all the launch arrival combinations that we could have, there were something like 10,000 of them.
And there seemed almost as many questions. What route would provide the most science? By what combination of instruments? How close in could the Voyagers fly and still survive? And how could Jupiter's immense gravity be best put to use? Calculating that answer really was a case of rocket science.
Jupiter's a huge planet. We're going to use it for gravity assist. You swing by the trailing side of a very large body. It changes the direction of the velocity vector. When you add that back onto Jupiter's speed around the sun, you get an increase of spacecraft speed relative to the sun, not to Jupiter, to the sun. And that gives us about 16 kilometers per second. It doesn't come for free. Jupiter is slowed in its orbit by 1 foot per trillion years because you have to preserve energy and momentum throughout the solar system.
A major decision was to make Voyager 1 the Daredevil mission. It was set on a course to fly closer to Jupiter on a riskier trajectory deep into the radiation zone. If the science objectives were met, the second Voyager would execute a more cautious approach, and one needed if the spacecraft had any hope of going on to Uranus and Neptune.
The pictures that are transmitted to us from the spacecraft come down in the form of black and white photographs. Different pictures, however, are taken through different color filters, and in certain circumstances we've combined them to make a full color picture. Here's an example of one of those. Again, it shows the great red spot. It was taken about a series of pictures taken a few weeks ago.
That was the most exciting time in my life, and I remember those days as if, they're all just, blazed into my head. Every day you're getting closer and closer to something you'd never seen before at that kind of detail. So every day you were learning something new.
Right. Now, how do you interpret that?
This was the first time that we'd seen time-lapse movies. We'd take one frame every 11 hours. And the rotation movies were neat because you'd see the planet rotating, but these zoom movies were really amazing because you'd sit there over one spot and just watch these structures, these storms, the red spot, and all these other things kind of evolve with time. And that was a really amazing thing. There was so much activity going on there. These cyclonic and anticyclonic flows, these creation of clouds and these disappearance of clouds and this incredible storm, which was the Great Red Spot, and this thing just whirling around as you're watching it.
Almost as amazing as these images were the animations that provided viewers with an entirely different perspective and identity with the Voyagers.
These spacecraft are millions and millions of miles away, okay? Sure, they're going to send back pictures. But wouldn't it be great if the public could ride along, could sort of be peering over the Hawking antenna, looking at the planets and moons coming up? That would make people feel a part of the mission. That would be a way to engage the public.
Computer graphics was just emerging, and Kohlhase learned of a young man named Jim Blinn, who had recently earned his PhD in this new field.
There's a famous quote from one of Blinn's old mentors. There are 12 leaders right now in computer animation, and Jim Blinn is 6 of them. Blinn developed these very sophisticated computer algorithms, which were at the time extremely cutting edge.
As time starts moving forward, Jupiter is rotating in the background. All the horizontal lines are the paths of the satellites as they go around Jupiter. Here we are flying in towards Saturn. We fly underneath the rings of Saturn, but we're underneath the plane of the rings, and so we're not going to collide with them, we hope.
These were just wireframe animations. When Blinn put textures and skins on the planets, the result for viewers of that time was spellbinding.
All of a sudden, they started getting this tremendous feedback about these fantastic animations that let you actually see what the spacecraft is doing as it zooms in towards these planets and their moons. So these computer animations were a great hit and actually contributed to this tremendous public response to the Voyager encounters. Pretty soon you have these people from Hollywood coming up to JPL to get demos of this new animation software that Blinn had developed. And then they go back and say, we can incorporate this into our movies. Over time, computer animation makes greater and greater inroads into Hollywood. And of course now, anytime you step into a movie theater, you're going to be bombarded with these CGI effects, computer-generated images, which trace back to what Jim Blinn was doing here at JPL in the 1970s for Voyager.
For 7 years we'd been preparing, and suddenly for a period of several months we were overwhelmed with a flood of discoveries, one after the other, many every day. One of the challenges we had in planning, because all this has to be pre-planned and all has to be loaded onto the spacecraft and then executed automatically. What do we look at? When? What do we observe at what time?
Ed Stone was, and remains, the Voyager project scientist, the only person ever to hold the position. It has proven to be a plum assignment, but Stone, a Caltech professor of physics, had to be convinced to take the job.
And eventually I realized that this was really an opportunity of a lifetime because we were going on a journey of discovery.
Stone knew that taking the position would mean coping with sizable squabbles among a science team numbering over 200. But his low-key temperament made him an excellent choice for reaching consensus when faced with competing interests.
We would occasionally have conflicts that seemed irresolvable. We would prepare a presentation for the project science group saying, these are the alternatives, and we have to choose one or some combination of two of them. Dr. Stone, at that point, would hear from each of the teams what their opinions was, and then he'd say, okay, this is the way we're going to do it, and that's the way we did it.
I think the point is that, we don't want to work the problem here. If there are some problems, there's an outside forum to do it. Sure.
It was a great training ground for learning how to handle conflicting science requirements. There's a phrase that shows up in discussing science conflicts. My science is better than your science. And if that's your only argument, you're not going to win. You've got to convince the other guys that you've got a point that your science is worth doing and it's worth trying to accommodate it. And that's what Ed was very good at.
Meanwhile, Bruce Murray was out promoting the flyby and its significance. Just as he had done for the first flyby of Mars, Murray arranged a public event at Caltech featuring the same panel of thoughtful speakers. The only difference was that this time, Arthur C. Clarke, author of 2001, appeared via a recorded message air-shipped from his home in Sri Lanka.
I'd like you to meet my friend Hal Jr., Christmas present from Hewlett-Packard back in 1969. Still going strong after nearly 10 years and showing as yet no signs of rebellion. When Bill Pickering was here for dinner the other day, he gave me this photograph taken from Voyager 1 in January, about 50 million kilometers away. And this is very much the view I had through my 18th Celestron last night.
And this is part of a remarkable historical transition which is happening in the late 20th century, in which we are for the first time learning the realities, not the myths, of our little swimming hole in space.
We are crossing a profound boundary in our own solar system. If I may borrow a Saganism, we are all guilty of inner solar system chauvinism.
Tonight, our eyes, our minds, our souls, our blood are moving out through the universe. 1,000,000 years from tonight, this evening that we're sharing together will be looked back upon by people who will say how fortunate those people were to have participated in this evening. So we have to relish every second, every minute, every hour of the evening and the morning to follow here, because we're part of history.
I remember being in the ops center at the first Jupiter encounter and seeing these pictures returned in real time, an image every 42 seconds, downlink from the spacecraft, at these odd-looking worlds. Just blew us away. And I really experienced the sense of discovery.
With me now is Dr. Torrance Johnson from JPL, also a member of the imaging team. Torrance, we've seen these incredible pictures. Would you care to give me a feeling what that means to you?
Well, first of all, it's a culmination of a long waiting period for all of us. What I wanted to see was what these places were really like as worlds, and they didn't disappoint. Every one of these objects was different. They weren't all just cratered up icy mud balls. Callisto was the one we got a good look at first. It looked sort of like what everybody thought outer planet satellites ought to look like. It's sort of a dark surface with some bright spots on it that we knew were ice, and craters every place. Ganymede really started getting our attention because there were places on Ganymede that looked just like Callisto. But then there were places where that surface had been replaced by bright grooves and bands and a much brighter ice.
There is always a trade-off on the encounter. And it turned out that the trade-off for the first encounter was not getting a very good close approach of Europa. Almost certainly has a global ocean. We didn't know that at the time. So there was a real mystery as to what the surface was like.
As we approached Io, we saw an object that looked unlike anything we had ever seen before. In fact, we have not seen anything like it since. We did not understand what we were looking at all. It was so different than anything we had imagined. And it was only as we were flying by Io that a navigation image was taken, that is, an image taken with a deep exposure to find the stars in the background, that a navigation engineer, Linda Morabito, noticed that there was this large plume off the limb of this little moon of Jupiter.
From the center of the satellite, we look out in all directions, and knowing the surface reflection characteristics of the satellite, we can in fact convolve what we expect the shape of the drop-off of the limb to be with the actual data. And where the convolution has a peak response, that is where, in fact, the edge of the satellite is.
When I did some special processing on the picture to bring out the very dim image of the satellite, this enormous, anomalous object emerged. And I just kept thinking, what is that?
What Morabito saw beyond the edge of Io looked like a ghostly moon.
I just kept saying, what's that? What's that? And I couldn't find an answer, but I had to keep asking. And even in the first initial seconds, there's nothing like that, like something unexpected, that large, that anomalous, that coherent in its appearance. It's unforgettable, beyond anything a person could ever expect.
The phantom moon turned out to be a gigantic plume of gas and dust, shooting skyward from a volcano.
And that was the first indication that this is the most volcanically active body in the solar system, 100 times more volcanic activity than Earth. And yet it's just a small moon orbiting this giant planet.
A colleague urged Morabito to write down how it felt to have made science history.
I would glance up at a monitor to see Jupiter absorbing the beauty of Jupiter's cloud patterns. And then there was Jupiter's moon Io. No one could have imagined Io. I was very surprised by one of these post-encounter frames. I sensed that I was seeing something that no human being had ever seen before. It was the stuff of dreams.
4 months later, it was Voyager 2's turn at the giant planet. This second look at the Jovian system featured a much closer flyby of Europa and a 10-hour volcano watch on Io. All told, the two Voyagers took more than 33,000 images of Jupiter and its major moons. What these images and the other science results revealed was an exotic system that was not only vast, but beautiful, and almost beyond imagining.
I'm determined as President to make sure that the United States always maintains its leadership in space exploration.
1 year after Voyager 1's encounter with Jupiter, Bruce Murray was among a small entourage invited to the White House, where President Jimmy Carter announced Voyager had been awarded the prestigious Goddard Memorial Trophy.
I think the whole world was enraptured on 2 occasions in 1979 when the Voyager passed by our largest planet, Jupiter, and sent back some absolutely remarkable photographs that...
The ceremony was an ironic reminder. Despite a claim for planetary exploration that reached all the way to the Oval Office, the pipeline for future planetary missions was meager, as were prospects of keeping intact JPL's skilled workforce.
JPL had built up this expertise over decades, and some of that expertise was acquired quite painfully over many years, and then to just see that walk away and go out the door was a very painful prospect for the lab's leaders, including Murray.
To keep the doors open, Murray began diversifying the lab's technical portfolio by addressing national needs in areas like energy and transportation.
But it was a low time in spacecraft employment, and it kept some talented people in storage for a while, if for no other reason it had its value in that regard.
The lab put its know-how to work exploring how solar panels could be used to meet everyday energy needs. Another hope in the midst of the oil crisis was to put all-electric and hybrid automobiles on the highway. And if the lab could build a nearly autonomous robot that could operate millions of miles away, how could that same know-how transport people on Earth without a driver? Working for the Defense Department was another area that the lab was tentatively exploring. But foremost on Murray's hope for the future were new planetary missions. He declared they could no longer be sold on science merits alone. Those kinds of missions Murray labeled gray mice. He wanted ideas that could also catch the public's imagination. Such concepts were deserving of an unusual name, and Murray gave them a colorful one.
Purple pigeons. And purple pigeons are the exact opposite of gray mice, right? You know, and purple pigeons also have the unfortunate element of not always being believed if you see one.
The pigeons included a rover on Mars, mapping cloud-shrouded Venus with radar, landing probes on Saturn's moon Titan and Jupiter's moon Ganymede, using ion propulsion to visit asteroids, bringing back to Earth rock samples from Mars, and Murray's favorite, rendezvousing with a comet. And not just any comet, but the most well-known of them all.
Bruce right away realized this was a very purple pigeon, and if you could really rendezvous with Halley's Comet, a once-in-a-lifetime opportunity, the government wasn't going to turn you down on that. NASA was definitely going to get approval to do that kind of a mission, whatever it cost.
The original idea for a mission to Comet Halley was the deepest color of purple. Solar sails were to be unfurled from the space shuttle spanning half a mile. Nothing even remotely like it had ever been flown.
How compelling an idea it was. I mean, the idea is basically impossible as we understood it.
Bruce loved the solar sail. He just thought it was romantic and really kind of a landmark in human history.
A mission to Comet Halley became the cornerstone of Murray's roadmap for the future. So was the idea of creating a national advocacy organization to drum up support for planetary exploration. A highly unusual decision for someone running a major NASA facility. To create the group, Murray teamed up with his longtime colleague Carl Sagan. What they needed was someone to run it.
So one day Bruce calls me into his office and says, so what's new? And so I start one sentence, and of course he cuts me right off and says, let me tell you what we're thinking of here.
Lou Friedman was a standout maverick among a sea of them at JPL. This engineer from the Bronx had once led a small group of JPLers who, on their own and without management's knowledge, had tried to sell not one, but a batch of missions directly to Congress and the White House.
And we didn't have any permission to do this, but we didn't know we needed permission either. You know, why can't you just call up somebody in the government and go to see them?
When Murray heard of this escapade, he had to be talked out of firing Friedman on the spot. But the episode left the clear impression that Friedman was not to be counted among the gray mice. His unorthodox style was just the quality Murray wanted in a new role.
And that's what led to the development of the Planetary Society.
The three men began patching together a network of grassroots support for exploring the solar system, just as a new president of the United States, with a very different agenda, was taking office. Just ahead was Murray's greatest crisis, and it would all take place as the two Voyagers swept through majestic Saturn. As Voyager 1 bore down on Saturn, the spacecraft was clocking nearly 1 million miles a day. And each day, Saturn revealed itself in some new way.
This faint one, this faint one.
Among the tremendous surprises there was that we could be, still more than 1 million kilometers away, and we could see structure in the rings.
All right. Look at that. That's nice. That's real nice. Let's see the other.
And one of the things I got involved in very early was the discovery of the spokes in Saturn's rings. And that was really super exciting.
Exciting and mysterious. Scientists could only speculate on what might account for such ghostly dark streaks. More and more, the rings were revealing their intricate and baffling structures. Some of them, scientists joked, seemed to defy the laws of physics. But they were all stunningly beautiful.
Well, here's the kind of experiment that's being done. It's just to lay down a series of images.
The rings themselves were much more complex than we imagined. The F ring, which is a very narrow ring, had these two shepherding satellites that had been predicted, but it was also kinked and braided.
For many scientists, the moon Titan was as important as Saturn itself. Titan is so large that if it orbited the Sun rather than Saturn, it would be called a planet. It was already known that this was the only moon in the solar system having a substantial atmosphere. This might be a place, some scientists theorized, that resembled the Earth before life arose. And that made this moon an irresistible target. But getting the best possible views came with a steep price. It required Voyager 1's tour of the planets to end at Saturn. That was the choice made, for Titan was deemed that important.
And we even had contingency plans if we had somehow or another failed with Voyager 1 to get good Titan data. There was a contingency plan changing Voyager 2 to pick up Titan, but abandoning the outer solar system.
There was this great hope that we'd be seeing down to the surface through this thick atmosphere. And we would discover, amazing things. As we got closer, at the time when we should have started to see features and resolution, it was awfully blank.
Although the hazy images of Titan were disappointing, the atmosphere was found to be, like our planet, rich in nitrogen. As hoped, this was in some ways a primordial Earth. After Titan, Voyager 1 swept underneath Saturn and then rose up out of the plane of the ecliptic and headed up towards interstellar space. 9 months later, Voyager 2 took its measure of the Saturnian system. Just as at Jupiter, the Voyagers found Saturn and its varied moons to be a mini solar system.
All the moons are different. They all seem to have had a geologic life. They were not just frozen, ancient objects heavily cratered. Each one had a unique story to tell.
Enceladus, with its diverse terrain, was one of the strangest and most mysterious objects in the solar system. The surface of Iapetus, for some reason, was an odd mixture of black and white, looking every bit like the Chinese symbol for yin-yang. The pitted surface of Rhea gave testimony to its ancient age and the violence this moon has endured. Mimas's massive impact crater had an eerie resemblance to the fictitious Death Star in Star Wars. Then there was Saturn itself, a world not nearly as serene as it might seem. Here, butterscotch storms raged at over 1,000 miles per hour.
Faster winds on Saturn than on Jupiter, even though there's less sunlight, less energy, faster winds. It's just one puzzle after the other.
By now, as one scientist put it, the bizarre had become commonplace.
The scientists knew that this was an epoch-making experience. Their knowledge of our solar system was advancing so quickly just because of these encounters. And I think the scientists realized this. They got caught up in this enthusiasm. Their curiosity was bubbling over. I think that ultimately is also part of what drove the public response, that the public sensed the scientific excitement. News crews start descending on JPL. You start having all these news vans out in the parking lot. You have the press conferences attended by hundreds of people from the media.
One can have gravitational instabilities where the rings...
Which was something I think that you didn't see previously for a lot of scientific events. I think that's fairly safe to say.
Normally, my experience had been getting press attention and wanting to tell my story. In this case, the press wanted us to tell the story.
They had become, in a sense, kind of space junkies. They liked the space program, they knew about it, and they became, in a sense, almost fans of JPL.
What is the albedo of clean eyes that is not exactly purely clean eyes and not exactly dirty eyes?
2 rows back, please.
Do you have a rough handle on what the orbital period or velocity of a theoretical moon in the Cassini division would be?
In the second row here, there's been a hand up for some time.
We seem to be losing the distinction between small moons and large ring particles. And I'd like to know if anybody is able to come up with a definition now of which is which. Those of us who like to count moons are starting to get worried.
It's purely semantics. I mean, after all, every particle in the Saturn ring system is, in effect, a tiny satellite in orbit around Saturn.
This was a wonderful environment to engage the media and therefore the public in the whole exploration and discovery and scientific process. And we needed to organize ourselves so that, in fact, we made maximum advantage of that opportunity to communicate what excited us, what we were learning, and what this process was all about.
This process works when you have...
That required a major change in how soon science results were announced to the world. What came to be known as instant science.
We did this by having these science meetings every day, and out of that science meeting, I would then decide which topics were ready for presentation to the press the next day.
It was taken August 15th.
August 15th.
And we were
10 days, 10 million kilometers out.
10.5. Right.
So that means we have a resolution of 20 kilometers per line pair. Okay.
You guys take a long time to get your developing done.
You know how to hurt.
But not all had gone well. When Voyager 2 emerged from behind Saturn, more pictures were expected. Instead, scientists and engineers were surprised to see only static on their monitors.
It's not there. It's not there.
Hundreds of reporters have been here at JPL.
That's the whiting. That's the whiting. What's all this noise?
The Voyager 2 scan platform has developed a problem. This platform is articulated in two dimensions, in the azimuth or rotation dimension, and at some point I'll go down and show you how that works. But basically,
hoping to get as much data as possible, scientists had worked the scan platform holding the cameras so hard that it froze, refusing to budge.
I was probably responsible for cramming in about as much as we could possibly fit. Here we were looking away from Saturn, all of this good science time going to waste because we couldn't point the cameras at the things that we wanted to look at.
See, right now we're attempting to send up a CCS load, a block of instructions up to the spacecraft. And we're having some trouble doing it right now.
There is not sufficient time to, even though the platform appears to be working better and better, to certify it in a way that would allow us to let the sequence issue azimuth and elevation slews.
I finally suggested if we could just swing the platform very slowly in a way that we know it'll work back toward the planet, we could at least keep it pointed there and collect data on the planet and on some of the moons during the time period that they were figuring out what the real problem was. They tried it, it worked. We got a lot of data that we would not have gotten otherwise.
I'd like to show you this first image. It's kind of special in that we had thought that we had lost all of the extremely high resolution data on Tethys. Well, this was acquired several hours after the scan platform problem occurred.
Just as at Jupiter, the Saturn flybys were an enormous success, both in terms of science and public acclaim. And because Voyager 1 had done its job, Voyager 2 had been able to stay on a trajectory headed for Uranus and Neptune. Once again, there was a treasure trove of data for scientists. And for the public, the images of Saturn had been captivating. One in particular had special meaning for Bruce Murray.
There's a picture, and it's up close, and it shows beautiful Saturn with the rings around it. You can see the shadow of the rings on Saturn. You can see that the rings are actually transparent. Elegant thing. But then as you look at it, you realize you're behind Saturn looking back at the sun and the Earth. That's a fantastic sense. You, the viewer, your brain, is behind Saturn. To me, that was a mind-blowing experience. It still is.
For Murray, the Saturn encounters were a bittersweet experience. For in the midst of this moment of triumph, JPL's very existence was in doubt. It would be the worst crisis in the entire history of the lab.
Bruce, I present this medal to you for outstanding direction and inspired leadership of the Jet Propulsion Laboratory in accomplishing the Voyager's epic mission, which gave mankind more knowledge of Jupiter and Saturn than produced in all of recorded history, and which shall serve as a lasting tribute to your distinguished service to the Jet Propulsion Laboratory and the National Aeronautics and Space Administration.
Bruce Murray was one of many honored by NASA between the two flybys of Saturn.
That's right.
For many who were at this JPL event, what's remembered most were not words of praise, but an unexpected message by NASA's new second-in-command, Hans Mark.
Hans Mark basically said, you ought to look for some other sponsors because NASA can't afford you anymore.
As a youngster, Hans Mark and his family had escaped from Nazi Germany. He had experienced the Battle of Britain when London was attacked by bombers and V-2 rockets. Making his way to the United States, Mark became a U.S. citizen and later a nuclear physicist whose expertise was the effects of atomic blasts. He went on to hold an impressive array of government positions, serving both Democratic and Republican administrations. Mark had been director of NASA's Ames Research Center, Undersecretary and Secretary of the Air Force, and director of the National Reconnaissance Office. He also could have competed with Murray to run JPL, but he took his name out of consideration. Planetary exploration, Mark thought, would not be an ongoing priority for the nation. The future in space, he believed, belonged to the shuttle, if there was any future to be had at all. For his overriding concern was a nuclear confrontation with the Soviet Union.
2 weeks ago, I attended the commencement exercises at Yale University, where my son was graduating. It was a beautiful day, and our distinguished guest here today, Professor Carl Sagan, was the principal speaker. Carl built the theme of his very eloquent address to the graduating seniors about two things that he considered to be the most important that had happened in the 4 years that the graduates were at the university. One was the fact, ladies and gentlemen, that 1,000 new nuclear warheads had been added to the world's inventory of weapons. And the other was that Voyagers 1 and 2 had explored for the first time the outer reaches of our solar system. Let me talk about the warheads briefly, because I just spent 4 years in the Department of Defense trying to come to grips with this problem. All of the approximately 1,000 nuclear warheads that Carl mentioned in his speech were added to the world's inventory by the Russians. There is no doubt at all that this great expansion of the Russian nuclear inventory represents a profound new challenge to this nation. Exploration is one of the measures of the worth of a society once its survival is assured.
JPL is basically surplus in Mark's view. What he thought JPL should be doing is going to work for the military. Here is this great resource of all these very capable expert engineers. Let's not just cast them aside. The nation has very pressing needs for military, including military space. Let's put JPL to work for the military while NASA concentrates on the space shuttle. And of course, Bruce Murray did not agree with that.
But Hans Mark's views reflected a new White House. Ronald Reagan had won a landslide election just weeks after the Voyager 1 flyby of Saturn. A major theme of Reagan's campaign had been to reduce the federal budget while increasing military spending that would create a new ground and space-based system to fend off a nuclear attack, what came to be known as Star Wars. These policies put more pressure on NASA as it worked to get the shuttle flying, and a huge challenge for James Beggs, Reagan's choice to run the space agency. Without enough money to go around, all planetary missions were now at risk. But Beggs had no wish to be remembered for ending the first explorations of the solar system. His requests to meet with White House officials to make his case for more funding were met with silence. Then Beggs tried a different tactic.
Beggs kind of pushed that back at the White House and said, okay, if you want to cut from our budget, we're not going to make the cuts. You're going to tell us where to cut. You're going to set the policy. And if you say that we have to have these cuts, and these cuts mean sacrificing JPL, which is a major institution in California, which is Reagan's home state. Then go ahead and make that cut. But we're not going to make that cut. You're going to make that cut if you're forcing these decisions on us.
Already, missions to study the Sun and Venus had been eliminated. The Jupiter orbiter, now renamed Galileo, was in danger of being canceled. And the press was reporting that the Voyagers might be turned off, never to be heard from again. If that happened, there would be no need for the world's only deep space communications network. It would be dismantled. The Planetary Society launched a letter-writing campaign directed at the White House, to no effect. Thousands of unopened letters were simply passed on to NASA for a form letter response. Murray next decided to take a different, more cordial approach. If White House decision-makers were to experience firsthand the thrill of Voyager, witness the press support, and sense the public's enthusiasm, that might change their minds and save planetary exploration. Murray succeeded in getting Ed Meese, Reagan's close friend and a presidential advisor involved in space policy, to come to the second Saturn encounter. Inside Mission Control, as data from Voyager 2 streamed back to Earth, Murray made his pitch. Why would America relinquish its leadership in deep space to the Russians? For what earthly reason should the United States give up the chance for Voyager 2 to explore Uranus and Neptune for the first time ever? And still ahead was the opportunity to visit for the first time a comet. A mission to Halley's Comet would attract the attention and praise of the world. And that idea had already caught on with the media.
Jules? So as I understand it then, Mr. Beggs, you're saying that if the mission makes sense, if Bruce and his team can prove to you a reasonable chance of our spacecraft bringing back a sample, you will do the Halley's Comet mission. Look at me. I didn't quite say that. No, I can handle this.
Jules, don't give me too much help.
Jules, if you're looking for an announcement, you're not going to get it. Follow-up question, though, Mr. Beggs.
The decision about Halley's Comet came 4 weeks later, and then there would be no laughter, and no mission by the United States to the famous comet. Murray took the news hard. He later called this moment the lowest point in his life.
There was a special irony at JPL, and a special irony for me personally, since how deeply I believed in planetary exploration. And the greatest exploration in the 20th century, certainly, and maybe since Captain Cook, was going on. It's the very time that the program was being strangled to not be able to have launches for a long time afterwards. And so the contrast between those two was personally very difficult for me.
As a beginning, let's review what I call Black September, which was it was a bad month. It was only in literally just a month after the Voyager encounter at Saturn. The first thing, a very bitter pill, was we were unable to get the U.S. Solar Polar spacecraft restored. We were at the same time trying to get the Halley Intercept mission introduced into the budget, and that was also unsuccessful. So that was a very, very disappointing period. But then there were all these rumors in the newspapers. The DSN was going to get shut down, perhaps. Voyager was going to be silenced. We were going to send a lobotomy command to it. Galileo was going to get canceled. There was even a question of whether JPL's status as a NASA center was in jeopardy. And there were going to be massive layoffs, or the concerns about that. So I guess the question you should ask, and certainly one I ask, is what the hell's going on here? And you have to read something into that the United States is backing away from being number one in deep space.
After recounting Black September, Murray went on to put the best face he could on a major announcement.
And we're on a new trajectory now. And JPL is changing with it, and it must. JPL must evolve.
Hans Mark had been urging Murray to forge a strong partnership with agencies responsible for U.S. intelligence satellites. But Murray chose a different path. After getting Caltech's approval, he struck an agreement with the Army to develop battlefield coordination systems, work which he believed would be less classified and would have less of an impact on the lab's culture of openness.
And what I got the support for was to increase the fraction of work at JPL for the Defense Department from its current 6% to perhaps 30%, a significant one.
Taking on defense work was exactly what Hans Mark had been pressuring Murray to do. In his memoir, Murray put it this way: Mark's vision of the future was coming true, and I had become a character in it. The climax to this drama came when Mark returned to JPL with a blunt message. In a meeting in front of the lab's senior leadership, the NASA deputy administrator took Murray to task. He declared that Murray's obsession with planetary missions and stubborn reluctance to embrace defense projects had put JPL at great risk. Murray was stunned by the public dressing down and what was a blunt, unmistakable message of no confidence.
They wanted you to support the program. Loyalty above judgment. Ever heard that before?
Good morning.
3 months later, on April 2nd, 1982, on the 6th anniversary of his directorship, an emotionally exhausted Murray addressed the laboratory.
The last several years have been especially hard on dreamers and visionaries like so many of us at JPL. Now that we have passed the nadir point, recognized a change, shifted direction slightly, negotiated the initial arrangements to permit a new direction for JPL, the fact is that the director himself has got to ask himself, is he willing to lead JPL entirely through the next decade? But that time has come, and I have notified President Goldberger of my intention to step down as JPL director later this year, and Mr. Beggs has also been notified.
After announcing his resignation, Bruce Murray stayed on another 3 months, but left JPL before his successor was in place. Murray returned to Caltech as a professor and continued his involvement in the Planetary Society until his retirement. He died in 2013 at the age of 81. Murray had been best at seeing the big picture. His criticisms of the space shuttle were tragically borne out. The loss of Challenger led to a dismantling of the policy that the shuttle would deliver all U.S. payloads into space. He had once said that running a lab is easy, creating the future is the hard part. But Murray's vision for JPL was not realized. By his own assessment, he had at best led a strategic retreat from JPL's golden age. It may have been all anyone could have done. And while one crisis after another had thwarted his plans, many of his purple pigeons would eventually fly, years later. Venus would be mapped with radar. Ion propulsion would be used to propel spacecraft to comets and asteroids. An orbiter would circle Saturn, and a probe would be dropped onto the surface of its moon Titan. And rovers would rove on Mars. At the time of Murray's departure, he could take comfort in knowing that JPL was still exploring the solar system. The mission to Jupiter had survived, and the Voyagers continued on with their adventures. Ahead were Uranus and Neptune, and all that existed beyond. What awaited the Voyagers, one could only guess and hope. In 1982, the same could be said for JPL.